I want you to imagine just for a second that you're going back to the fourth grade.
Oh, wow. Okay.
Yeah, you're sitting at a desk that's, slightly too small for you. You're clutching a freshly sharpened pencil, and you're staring down at a science review sheet.
Right.
But instead of just memorizing a few basic facts to pass a test, what if the answers on that sheet actually outline the fundamental rules that power the entire universe?
It's quite a shift in perspective, really, because when
Mhm.
we think of elementary school science, we usually just picture like baking soda volcanoes or memorizing the names of the planet.
Exactly.
We rarely appreciate how profound those core concepts really are once you look past the basic vocabulary.
And that's exactly what we're going to explore today. We are taking a deep dive into an actual fourth grade science exam.
Which is so fun.
It is. Specifically, we've got a final review script from the popular education channel, Mr. Radlab. And on the surface, it's a study guide for a module called Unit 3, Energy and Devices. But if you really read between the lines, it's actually an instruction manual for how reality operates.
It really is.
So our mission today is to master the concept of energy chains. We're going to figure out how to avoid the exam pitfalls that trick 10-year-olds, and honestly, most adults, and apply these rules to everything, from your living room gadgets to rovers rolling around on Mars.
What's so fascinating about diving into this specific material is that sometimes the most complex scientific truths are actually best understood when they're distilled into a lesson for a child.
Oh, absolutely.
When you strip away all that dense academic jargon and just look at the raw mechanics of energy, it completely changes how you view the physical world.
Well, let's get right into those mechanics, because before we can talk about how our smartphones or our blenders use energy, we kind of have to understand the ground rules.
Right, the basics.
Yeah. The review script starts with what it calls the ultimate rule, the law of conservation of energy. Right. And the core concept here is that energy cannot be created out of thin air, and it cannot be destroyed into nothingness. It only changes form.
Yeah, and the source material actually uses a really helpful visual for this.
Oh, the costume thing.
Exactly. It describes energy as this entity that's always the exact same thing underneath. It just, changes its costume.
I love that.
Right. You're never making energy when you flip a light switch, and you're certainly not killing energy when you turn it off. You are just forcing it to swap its electrical costume for a light costume.
But this is exactly where the exam trips people up. There's this major pitfall, noted in the review, where students wrongly think that energy gets used up.
Yes.
And frankly, I completely understand why a 10-year-old would write that. I mean, if I run my flashlight until the battery dies, my intuition tells me the energy is just gone.
Right, it vanished.
Exactly.
It's a completely natural assumption because, from your perspective as the user, the device stopped doing its job. The
Right.
flashlight is dark, but the energy didn't vanish. What actually happened is that the energy transformed into forms that are simply less useful to you in that specific moment.
Less useful. Okay.
Yeah. A lot of that battery's energy actually transformed into heat that just escaped into the surrounding air.
Wow.
So the energy is still very much real. It hasn't left the universe. It's just dissipated. It put on a thermal costume and drifted away from the flashlight.
So if energy is just constantly shifting around, never dying but never being created either, it has to come from somewhere initially, right? Like, where's the cosmic starting point for us?
For almost every single thing we do, the primary source of energy is the sun.
The sun.
Yeah. The light radiating from our local star is the absolute starting point for the vast majority of energy chains on this entire planet.
Now, I easily grasp how the sun powers, like a solar panel. That's a very direct line.
Right.
But the review goes further and states that the sun powers fossil fuels. And if you ask the average adult how a lump of coal gets its energy from the sun, I guarantee most would draw a blank.
Oh, completely.
So how does that mechanism actually work?
Well, it requires zooming out and thinking across vast stretches of time.
Okay.
Let's trace the actual mechanics. A plant grows by capturing solar energy through photosynthesis, right?
Right.
But what is it actually doing? It's taking that sunlight and using it to forge chemical bonds. It takes carbon dioxide from the air and locks it into its physical structure.
Oh, wow.
And then millions of years ago, ancient forests of these plants died and sank into swamps. Over eons, extreme heat and pressure compressed them into fossil fuels like coal and oil.
Wait, so the carbon bonds inside the coal are basically acting like a massive ancient battery for the sun's energy.
Exactly.
That is wild.
Yeah. When you burn a piece of coal today to generate electricity, you are breaking those bonds and literally releasing ancient sunlight. sunlight that was trapped underground for hundreds of millions of years.
It's crazy to think that when I, turn on an electric space heater in my bedroom, I'm literally warming the room with sunlight that hit the Earth millions of years before the dinosaurs even existed.
It really is mind-blowing when you frame it like that.
And the review points out this applies to the water cycle too, which I'm assuming is also driven by heat.
Yes, the mechanism is entirely solar. The sun's thermal energy heats up the oceans, right?
Okay.
That heat increases the kinetic energy of the water molecules until they literally break apart and evaporate into a gas.
And then they rise up.
Exactly. As they rise and cool, they create weather patterns, wind, and rain, which fill rivers.
Oh, I see where this is going.
Yeah, those rivers flow downhill and spin the turbines in our hydroelectric dams. So even the kinetic energy of a rushing river is, at its root, solar energy that just changed its costume.
That makes so much sense. Okay, so if you were taking this test today, here is where you would need to prove you understand this flow.
Right, the energy chains.
Exactly. You have to be able to draw an energy chain. The review is very specific. You always start with the sun, and you use arrows to show the direction of the transformations, pointing from one costume change to the next.
Yeah, the arrows are important. They aren't just lines. They represent the actual cause and effect of the energy moving.
Right, so mapping it out logically is key. Let's see how this works in practice. There's a practice question in the review script that asks, what is the scientific term for the energy produced by a battery-powered toy car?
Okay.
And the answer at once is kinetic energy. To get there, the kids are taught to look for the keywords stored versus moving.
That distinction is crucial. I mean, identifying whether energy is patiently waiting or actively doing work is basically the entire foundation of mechanical physics.
Right. I always think of it like a classic jack-in-the-box.
Oh, that's a good one.
Yeah, like when you turn the crank, you're doing work. Then, when the lid latches shut and the spring is just squished inside, that box is full of potential energy.
It's stored.
Right. It has the potential to do something.
Yeah.
But the absolute second you unlatch the lid and the toy springs out, that stored energy instantly becomes kinetic energy.
Because kinetic means moving.
Exactly.
That's a perfect analogy. So let's take that understanding and map out the full energy chain for that toy car, just like a student would have to draw on the exam. Keeping your jack-in-the-box in mind, of course.
Okay, so on paper, we start with the sun. Solar energy radiating through space.
Right.
Arrow pointing to Earth. That energy is captured by ancient plants. Arrow pointing to fossil fuels. We burn those fuels to generate electricity. Arrow pointing to a battery factory. Now, inside the battery, the energy is chemically charged. It sits on the shelf, holding chemical potential energy.
Just like the jack-in-the-box with the lid closed.
Exactly. The energy is locked in a chemical state.
Yeah.
Just waiting for a circuit to be completed.
Right.
Then, a kid puts the battery in the car and flips the switch to on. Immediately, the chemical potential energy transforms. Arrow pointing to electrical energy flowing through the wires.
Yep.
That electricity reaches the motor. The wheels spin, and the car zips across the floor.
Yeah.
The final arrow, the output of this chain, is kinetic energy.
When you lay it out step by step like that, the sheer complexity of what it takes to make a little piece of plastic roll across a kitchen floor is staggering.
It really is.
Solar to chemical to electrical to kinetic.
Yeah. And it makes perfect sense for a toy. But let's bring this out of the playroom and into our adult lives. What happens when energy powers our daily household devices?
That's a great question.
Because we plug things straight into the wall where the energy transformation is, I don't know, way more aggressive.
Right. So to analyze household devices for this exam, you have to establish two critical terms, input energy and output energy.
Okay.
Input energy is basically the fuel. It's the consumed energy that goes into a device to make it work. So for an electric fan, the input is electricity.
And the output energy is the energy produced by the device to perform its main intended function.
Exactly.
So if you turn on a desk lamp, you're looking for light energy.
Right.
That's the job you literally hired the lamp to do.
Right. But, and this is the catch, it rarely produces just the output you want, which leads us to the concept of useful versus wasted energy.
Oh, yes. There's a brilliant practice question that illustrates this perfectly. The review asks, what happens if you use an electric hairdryer for a long time?
A very relatable scenario.
Right. And the correct answer they want is that the electrical energy transforms into three things: thermal energy, kinetic energy, and sound energy.
This is a classic complex energy chain, and figuring out which of those three outputs are useful and which are wasted is a massive part of the curriculum.
Well, let's look at the hairdryer's job. You plug it in, so the input is electrical. The main job is to dry your wet hair. So the thermal energy, the heat, is obviously extremely useful.
Right.
And the kinetic energy, the physical fan blade spinning to blow that hot air, is also extremely useful.
Yeah, but what about the third output?
The sound.
Right, the sound energy. Does that incredibly loud whining noise actually help dry the water off your hair?
Not at all. It just annoys everyone else in the house.
Precisely. Because it doesn't contribute to the main function of the device, it's scientifically categorized as wasted energy. The energy isn't destroyed, remember our conservation law, but it has transformed into a state that is completely useless to the task at hand.
Which brings up one of my absolute favorite parts of this review script. It specifically points out a major trap that students fall into regarding this exact concept.
Oh, the washing machine one.
Yes. Apparently, a lot of kids think the sound energy coming from a washing machine is useful energy.
Which is so funny.
It is, but I kind of see the logic. Like when you're a kid, you hear this massive machine churning, sloshing, and vibrating.
Right.
It sounds like it's working incredibly hard. It sounds like it's literally fighting the dirt.
Yeah, it's a very logical leap. We associate loud mechanical noise with effort and productivity.
Exactly.
But scientifically, it's totally incorrect. A washing machine's only job is to agitate water and soap through fabric.
Okay.
That requires kinetic energy to spin the drum. The mechanical humming, the vibrations rattling the floor, the splashing sounds, none of that sound energy is physically lifting a grass stain out of a pair of jeans.
Right, right.
Therefore, every single decibel of that sound is entirely wasted energy.
There's another daily example the review uses that I found fascinating, and it's why our phones get warm.
Oh, yeah.
Like you're playing a graphic-intensive game, or maybe you're on a really long video call, and the back of your phone starts to feel hot against your hands.
It's all in there.
The source says this is wasted energy caused by friction. But I have to push back on that a little, or at least ask you for clarification.
Sure.
When I think of friction, I think of brake pads on a car, or like gears grinding. There are zero moving mechanical parts inside a smartphone. So how is friction generating heat?
That's a great observation, and it requires looking at things on a microscopic level.
Okay.
It's true there are no physical gears spinning in a smartphone, but electricity itself is the movement of electrons.
Right.
As your phone's processor works harder to render a video game, it's forcing millions of electrons through incredibly tiny microscopic pathways in the silicon chips.
And they don't just flow perfectly smoothly, I assume.
Exactly. They encounter electrical resistance. As the electrons navigate the crystal lattice of the silicon, they literally collide with atoms.
Oh, wow.
Yeah, they bump and rub against the structure of the chip itself. In physics, this electrical resistance acts incredibly similarly to mechanical friction.
That makes total sense.
Just like rubbing your hands together vigorously transfers kinetic energy into thermal energy, the resistance inside the microchips transfers the electron's energy into heat.
And since I bought my phone to, send texts and watch videos, not to act as a winter hand warmer,
Right.
that thermal energy is, by definition, wasted.
Yes. Anytime a device gets hot when it isn't specifically designed to be a heater, or makes noise when it isn't designed to be a speaker, you are witnessing wasted energy escaping into your environment.
So cool. Well, we've spent a lot of time looking at how these rules govern our living rooms and kitchen appliances.
We have.
But to really appreciate how robust these laws of physics are, we need to test them in the extreme. We need to look at an environment completely devoid of wall outlets and replacement batteries.
Oh, you're talking about taking these fourth-grade concepts into outer space.
Exactly. The final section of the review focuses on the Mars rover.
I love this part.
There is a specific practice question that asks students to give reasons why the rover Curiosity uses solar panels instead of ordinary batteries.
Right.
And the answer the exam requires is simply, because it is impossible to replace batteries on the surface of Mars.
It sounds almost too simple, doesn't it? Like a trick question.
It really does.
But the engineering implications of that single sentence are staggering. We have to really grasp the context of deep space limitations here.
Okay.
Mars is, on average, over 200 million kilometers away from Earth. If your TV remote dies, you walk to the kitchen drawer and grab 2 new AAs.
Right. Easy.
But if a multi-billion-dollar rover runs out of power on Mars, nobody is coming to help. It basically becomes a permanent stationary monument in the dust.
So the energy chain has to be entirely self-sustaining.
Yes. It relies completely on that cosmic starting point we talked about earlier, the sun.
Mm-hmm.
The rover is equipped with highly advanced solar panels that act as a direct energy trap. They capture the incoming solar energy and immediately transform it into electrical energy.
But wait, Mars has nighttime.
Yeah.
And it has massive global dust storms that
Yeah.
block out the sun for weeks.
Right.
If it only relied on immediate solar to electrical transformation, wouldn't it just die the second a cloud rolled over?
Which is exactly why the energy chain doesn't stop at the solar panel.
Yeah.
That newly transformed electrical energy is fed directly into the rover's internal rechargeable batteries.
Oh, I see.
Yeah, the energy changes costume again, becoming chemical potential energy. It sits in those batteries, stored and waiting.
Okay.
Then, whether it's the dead of night or the middle of a dust storm, when the rover needs to drive over a crater or drill a rock sample, it taps into those batteries.
Turning the potential energy back into kinetic and electrical output.
Exactly, allowing the machine to function for years without a human ever touching it.
Now, there's a fascinating misconception that the source brings up about how we actually control this rover.
Oh, the remote control thing.
Yeah. I think a lot of people picture a scientist sitting at NASA with a joystick, driving it around like a remote-controlled car in real time.
Right, like push forward, the rover moves forward.
Exactly.
It's an easy assumption because we're so used to instantaneous communication here on Earth. I mean, when you click a link, a page opens instantly.
Right.
But you have to remember that 200 million kilometer distance, the absolute speed limit of the universe is the speed of light, and radio signals travel at that speed.
Which is fast, but
not instantaneous. Even going as fast as physically possible, a command from Earth takes roughly 5 to 20 minutes to reach Mars, depending on where the planets are in their orbits.
wow. So if a scientist on Earth sees the rover heading toward a cliff and pushes the joystick to turn left,
Yeah.
the rover won't even receive the command for 20 minutes. And it takes another 20 minutes for the rover's confirmation to reach Earth.
Exactly. By the time you see the cliff on your monitor, the rover would have driven off at 40 minutes ago.
That is terrifying.
Because of that extreme distance, the rover cannot just be a simple toy awaiting remote input. It must be smart. It has to be semi-autonomous.
That makes total sense.
It uses its onboard sensors, powered entirely by that solar energy chain, mind you, to constantly analyze the terrain, make its own decisions, and keep itself safe while it waits for our severely delayed instructions.
It really puts the fragility of these space missions in perspective. You're trying to carefully manage the law of conservation of energy on a frozen desert 200 million kilometers away, where you literally cannot afford to waste a single drop of it.
And it all relies on the exact same scientific principles that dictate why a 10-year-old's battery-powered toy car zips across the floor.
Amazing. Well, we've covered an incredible amount of ground today. Looking at this fourth grade review really does shift how you view the world.
It definitely does.
We mapped out how the sun is the ultimate battery charger for almost everything on Earth. We explored the microscopic friction that makes our smartphones hot. And we saw how those exact same rules allow a sophisticated rover to survive alone on an alien world.
It just goes to show that the basic rules of science aren't just, trivia to be memorized for a multiple choice test. They're the actual operating system of the reality we live in.
Absolutely. As we wrap up this deep dive into the Mr. Sadlab final revision, we like to leave you with something to ponder.
Yes.
Given everything we've talked about today regarding how energy moves.
Think about this. If the law of conservation of energy is truly absolute, if energy never disappears and is only ever transformed, that means every single bit of wasted heat currently radiating off the back of your phone,
Oh, wow.
and every single annoying sound wave vibrating out of your noisy washing machine doesn't just vanish when you turn the device off.
It goes somewhere.
Right. That energy has simply left your device and is out there rippling through the universe in some microscopic, dissipated form.
That is wild.
The energy you use today is forever altering the physical environment around you until the end of time.
Well, on that mind-bending note, thanks for exploring the rules of the universe with us today.
Yeah.
Until next time.